Welcome to the 7th lecture in quantum field theory. Now we will begin discussing the Lorentz transformations, and this is of course going to be a very important topic, very long topic. So if we want to be able to understand whether or not the Dirac equation that we came up with is actually a Lorentz invariant, we need to understand what all of that even is. So we will take an entire chapter to talk about all of that. And right now we will begin just focusing on the Lorentz transformations. And we will do this from a relatively basic entry point so that if you don't know much, I mean, of course you need to know like some general notions. So of course you have to understand what they are, just the basic principles of special relativity. And from there we can work together just step by step. So the first thing that we need to understand is just the whole concept of these transformations that can happen to sets of coordinates. So let's begin by thinking back just to regular old rotations. So let's say, for example, that we have some coordinate x1, x2, x3, or x, y, z. So for example, if we want to transform the x1 coordinate, which is x, let's say that we apply a rotation, so under rotation, just so that we can build upon some things that you may already know. So if we do a rotation, the way we do it is we multiply cosine of the angle of rotation times x1 minus sine of theta times x2, which would be y if you're using just regular names. And then the y transformation, right, or x2 prime is now sine of theta times x1 plus cosine theta times x3. And since what we have here is a rotation around the x3 axis, that means x3 is unchanged. Okay? That's the way that we usually write these rotations. So this is something that we can now write much more compactly. So if we say this entire thing here is going to be simply x prime, then we can write this as x prime is equal to, and what we have right there is the product of a matrix, which is cosine theta minus sine theta, sine theta, cosine theta, and then we have a bunch of 0, 0, 1, 0, 0. And this is our rotation matrix. And then we still have just this column vector x1, x2, x3. So multiplying through, of course, we see that we get what we had before. So we multiply here the first row with the column. We get cosine theta x1 minus sine theta x2. And then the second one, sine theta x1 plus cosine theta x2 and 0 times x3. And finally, x3 prime is equal to x3. So this is a nice compact way of writing it, which simply is x prime is equal to r times x. Okay, and that's a way in which we can generalize the notation that we have for when we don't actually want to write down the matrix explicitly every single time. So another important thing to note about these matrices, so this rotation matrix, for example, is that if you take its transpose and multiply it by itself, or rather just multiply the transpose by the original matrix, you get 1, right? We can easily check this. So the transpose here is simply cosine theta sine theta minus sine theta cosine theta 0, 0, 1, 0, 0. And now we multiply this by the original matrix. So cosine theta minus sine theta cosine theta 0, 0, 1, 0, 0. So now we multiply this and we get a new matrix. So let's see. Here we have cosine times cosine, so we get cosine squared of theta, and then we get sine times sine, so plus sine squared of theta. Then we get minus sine times cosine plus cosine times sine, which is going to be 0. Then we have, 0 times cosine, 0 times sine, so 0 as well. Then we move on to the next row, and there we get cosine theta times minus sine, sine times cosine, so also 0. And then in the next element here, we have minus sine times minus sine, so sine squared plus cosine squared. And 0, 0, 0, 1. And of course, cosine squared plus sine squared is 1, so we end up getting the identity matrix exactly like we wanted. Again, keep in mind that when we write this as this 1, we of course mean the identity matrix in the corresponding dimension, right? It's just a faster way. This would be just the identity. In this case, it's 3 by 3. But just so that you keep that in mind. Okay, so we can see that this is true, right? So the matrix is orthogonal. That's what this means. So when a matrix multiplied by its transpose gives you the identity matrix, this just means that the matrix is orthogonal. So orthogonal. And another important thing is that the determinant of R is equal to, let's see. So if you take the determinant here, you get cosine theta times the determinant of this. Or actually, that's the transpose, so we should be looking at this one. So we had cosine theta times the determinant of that, which is cosine theta, minus sine theta, so plus sine theta times the determinant, this would be of this and this. So sine times 1, so we just get sine squared. So we get cosine squared plus sine squared, which is equal to 1. Okay, so we have determinant 1. So that's also a very important characteristic of the rotation matrices. Now, something that's very interesting usually is to study the infinitesimal rotation or transformation in general. And why? Because, well, any transformation, or especially a rotation, maybe not any transformation, but any rotation, you can write it as just the sum of a lot of infinitesimal transformations, right? You just move it infinitesimally and again and again and again and again, and you can get any rotation that you want. So for that reason, it's interesting to write our transformation, but now in infinitesimal terms. So maybe we can just go up here, so and just write infinitesimal. So let's do it here, infinitesimal. So let's just write the same thing. So x1 prime, well, the cosine theta, if theta is very, very, very small, is simply 1. So x1, right? So this is, of course, this approximation. Then minus sine theta. Well, sine is basically theta when it's very small, but let's now just call it epsilon, this very, very small amount, just so that we keep with convention. And similarly, x2 prime would be epsilon x1, and cosine theta is still 1, so we get x2, and x3 prime as well. It's the same. So our rotation, our matrix of rotation in this infinitesimal case would be, so the rotation matrix, maybe let's say infinitesimal, would be 1 minus epsilon, 1, 0, 0, 1, 0, 0. So what we can see here is that we can write this in the following way. So whenever we have this infinitesimal rotation, we can write this as the identity matrix, right? So we can write this as the 3 by 3 identity matrix plus, then we have this 0 minus epsilon, 0, epsilon, 0, 0, 0, 0, 0 matrix, right? So that's what we can write it as. And that's going to be very, very interesting because that's actually going to be happening over and over again. We will see that again in the future. And of course, you can see that this matrix is going to be anti-symmetric, right? So it is anti-symmetric. It only has 2 elements. They are basically in reverse positions. One is in position, well, it depends when you start counting, but one is in position 1, 2. The other one is in 2, 1, depending on, or 0, 1 and 1, 0, depending on how you're counting. And you can see that one is just the other one, but with a minus sign. So it's evidently anti-symmetric. So that is just a quick introduction about working with rotations. Okay, and now we're going to do basically the same procedure, but with Lorentz transformations. Okay, so basically the same thing. That's why we went through this, because that way you can understand the process with something that you are hopefully already familiar with. So now let's go for a transformation in which any of our 4 vectors x mu, of course this is going to be valid for any 4 vector, but we are going to use x mu here, is going to transform into x prime mu. Okay, so that's what we're going with. Now let's write this down explicitly first. So this means that x prime 0, let's go for each coordinate, so x prime 1, x prime 2, x prime 3. So each one of these is going to transform. Now, how do they transform? Well, just pick up your old notes on special relativity and just write it out. So this is the time component. So this is just time. So that transforms as gamma times x0, which is, again, time. This would be like t prime. This is regular time. And minus gamma beta x1, which is usually x, right? But now just, there we go, x1. Then x prime 1, which would be how x transforms, is minus gamma beta x0 plus gamma x1. Okay, so of course note that whenever we are transforming, we are doing this Lorentz transformation, we know that it only happens in the time direction and also in the direction wherever you are currently doing the rotation. So if you are doing it in the x direction, y and z will be unaffected. If you're doing it in y, x and z are going to be unaffected, and so on. Right, and you can always align yourself such that you are in a single direction, right? If it's in a mixture, well, you just choose a new axis where the transformation points in the direction of one of your axes. So that means that x2 and x3 are unchanged. So now, just like we did before, we're going to write this out as a matrix. So this would be x prime 0, x prime 1, x prime 2, x prime 3. I don't like the way this 0 looks, so I'm going to quickly improve it. Okay, so this would be, now let's write the rotation matrix, right? This R matrix, which no longer will be called R, of course. Now we are in Lorentz transformations. So it's going to be called lambda, and it's going to have sub indices, super indices, depending on what exactly we're doing. So here we would have gamma minus gamma beta 0, 0, minus gamma beta gamma 0, 0, and then 0, 0, 0, 0, 1, 0, 0, 1. This is a 0, 2. Okay, so that is the transformation matrix. And then we have still, of course, our original coordinate. So x1, or rather x0, of course, it begins with x0. So x0, x1, x2, x3. So here you can just multiply through and see that you get exactly what we had before. Okay, it's just a more compact way of writing it down. And of course, don't forget that the gamma here, gamma is simply 1 over the square root of 1 minus beta squared. Now, something we want to do is just show that this is very similar to the case of the rotation. Okay, so what we will do here is call gamma is going to be equal to cosine, the hyperbolic cosine in this case, of omega. Now, don't worry too much about how people came up with this. It's simply something you realize when you see, oh, this kind of looks like a rotation, but in 4-dimensional space-time. So don't bother yourself all that much for now with it. So let's just begin learning how to work with it step by step. And we will define gamma beta as the hyperbolic sine of omega. Now, why do we do this? Because that way we are going to get a matrix that looks like this. So our lambda, I'm not going to use any superscripts for now. So I'm just going to say lambda, and there's going to be sub and superscripts, but for now, I just want to introduce the matrix itself, and then we will work with that. So we get, instead of gamma, hyperbolic cosine. Instead of gamma beta, we get sine, the hyperbolic sine. Another, that's way too far up. Another hyperbolic sine, and hyperbolic cosine, and then 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. And now if we take a look at this and we compare it with, let me zoom out, there it is, with our rotation, we had cosine, minus sine, sine, cosine. Now we have, it looks relatively similar, not 1-to-1, but we can definitely see some trace of similarities. Now, something that we want to do now is just think of this parameter omega, right? What are the possible values that our omega can have? So if we defined our cosine and sine like this, but keeping in mind that, that gamma is simply 1 over the square root of 1 minus beta squared, beta, we know, can have values that range from -1 to 1, depending on which direction you're moving. And that just means that our parameter omega, right, keeping in mind, so if you do it, you would have beta over 1 minus beta squared. So maybe looking at the sine, for example, we get that omega would be the inverse hyperbolic sine of beta over square root of 1 minus beta squared. So we can here see, knowing that the hyperbolic sine can go all the way from minus infinity to infinity, and those values are exactly met at the values that we have in here, which is also from infinity to minus infinity, we can see that, since beta is between -1 and 1, the possible values for omega are going to be between, I need a bit more space, I guess. The possible values for omega are between minus infinity, I guess, just like that, omega and infinity. Okay, so you can just do that by plugging it in. So 1 minus 1, here for example, if beta is 1, you would get this 1 over 0, which tends to infinity, to positive infinity, and the hyperbolic sine inverse of plus infinity is going to be also plus infinity, and in the other case you just get a minus sign, so that's where that comes from. Okay, so using that, we will now write this transformation. So if we have some x mu, so x prime mu, so these are the new sets of coordinates, we had some other set of coordinates and we applied the Lorentz transformation. So in order for this to happen, we need of course a mu up here, and we now want this to contract. So we write the nu down here, and we usually do it staggered. So notice that underneath the mu, there is nothing. Above the nu, there is nothing. Because by convention, this here is going to indicate the row number, and this here, the nu, the second one, not necessarily nu, is going to be the column number. Okay, so that's why it's important that you keep them apart. Sometimes you will have something like lambda nu mu, right, where the first one is down here. And that's, well, we're going to get into that case very soon. But just keep that in mind, okay? So here the nus are going to contract, and you end up, of course, with your index up there. And that simply means that the matrix that we had here, and I just realized that this kind of looks like a 0. It isn't 0, I just meant that to be like empty space, right? So now we can write this as lambda mu nu. Okay, so the question of course would be, well, what about lambda mu nu, or nu mu if you want to do it the other way around? So what if we do it lambda and then first one down here and then one up there? Okay, so that's a very reasonable question. So what we do here is we're going to have to, well, we need to lower the mu and raise the nu. And how do we do it? Well, we simply do it by applying the metric. So if we want to lower mu, what we need is eta with a mu down here, and then the name of the new name for the index, which you can choose whatever. I'm just going to choose lambda. So this one is going to lower the mu. And then we need eta, and now nu, right, which that's going to contract with the nu, and raise it, and then we just take a new name, I don't know, rho. And now, of course, we need to have lambda with the indices up here, lambda, lambda rho. Okay, so this lambda will contract with the lambda, rho will contract with the rho, and we end up getting lambda mu nu. So that is in terms of just, writing down the tensors itself, right? But let's actually maybe multiply this, because at least I think that it's always good to keep in mind what everything looks like. Now, here is a very important step that it is confusing, and it was confusing for me when I was learning this. So something that's very important, when you're just writing this out in matrix form, you have to keep in mind, oh, does this commute with this? Does this commute with that? What can you move where? But when you are writing this as a matrix form, you have to also keep in mind where the correct positions are for multiplication. What do I mean by that? So for us to be able to multiply this, what we do is that we need to have our different letters side by side. Okay, so that means I want eta mu lambda. I'm going to keep it there, and I'm going to commute this with this, right? Because both of them are simply numbers. You can just move them around. I mean, at the end, because they are the lambda roth element of this lambda matrix, for example. So here we have lambda, lambda, rho. So now we have lambda and lambda side by side. So when we do that multiplication, it's all going to be good. And now we still have this. So eta new row. Okay, but here we don't have them side by side, so the multiplication there is not going to be quite okay. I mean, this is the metric, so in this particular case it's going to be the same, but in principle what we would have to do here is change the indices, but because it's asymmetric, the metric is symmetric, then yeah, you can just change them without any sort of consequence. So you can just write this as row new. And with this, we are now ready to actually begin multiplying. So lambda mu nu is going to be eta, so the metric 1, 0, 0, 0, 0, minus 1, minus 1, 0, minus 1, 0, 0, 0, 0, 0, 0. And then we have our lambda matrix. This is going to be, I already have it right there, so cosine, minus sine, cosine. So hyperbolic cosine of omega minus hyperbolic sine of omega minus hyperbolic sine of omega cosine, hyperbolic cosine of omega. So 0, 0, 0, 1, this is a 1, 0, wait. I think I'm missing, yeah, so it's, okay. I was way too, yeah, I skipped a column, so that's why I'm running into trouble. So this is 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. There we go. And finally, another metric. So 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, minus 1, 0, 0, 0. Phew, okay. So now let's multiply through. So we, of course, begin with these two matrices. So here we have 1 times the hyperbolic cosine, so we get hyperbolic cosine of omega, and 0 times everything else. Then here on the second row, we have the same thing. You simply multiply by 1. But now, in this element, which is the product of this times this, right, we get 0 times cosine minus 1 times minus sine. So we get positive hyperbolic sine. And then in this element, which is the product of this row, column and this row, we get 0 times minus sine, minus 1 times cosine, so minus hyperbolic cosine, 0, 0, 0, 0. And then we have minus 1, right, from this, and from the other one as well. So minus 1, minus 1. Times, well, 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, minus 1, 0, 0, 0. And now we multiply these two together. So, again, this is lambda mu nu. So lambda mu nu, this is going to be explicitly, right, just that's what we're doing. We're simply finding the explicit form, hyperbolic cosine, so cos omega. Then we have this times this, so we get positive sine, so sinh omega. Then we have this times 1, so we get sinh here as well. And then this times this, we get plus, so we get cos. And then minus 1 times minus 1, so 1, 1. So this is what this matrix looks like explicitly, in case you ever feel the need to use it. And you can see, of course, that it doesn't differ from when you write lambda mu nu, right? Mu upstairs, nu downstairs. So they are not the same, so be careful, okay? So that's how they are defined. That's a very important step. So we have to be very clear here, because what we found, this lambda mu nu here, this is the transpose of the original lambda mu nu that we had, where is it again? Up here. Okay, so that's very important. Notice that the transpose is not necessarily simply taking your columns and rows and exchanging them. It's not that anymore. Okay, so that was the case when we had matrices, but now with tensors, that is not necessarily the case. It could happen in some points, but that's not the case right here. So let's be very clear in terms of notation. So if we have some lambda mu nu, for example, like we had before, and we want to take the transpose, so transpose of lambda mu nu, what we get is basically we move this to the right and this to the left. Now here it may be perhaps a little bit confusing, the notation that I used, because I wrote down separately each one of the two cases, right, for the transformation of covariant and covariant vectors here, those expressions, but I used the same labels, right? So in principle, once we take the transpose of lambda mu nu, right, what we get is lambda nu mu. Okay, so first mu went to the right, nu went to the left. Okay, so that of course makes sense because this right here refers to the rows, right? The first index always refers to the rows, whether it is up or down, and the second one refers to the columns by convention. Okay, in principle, it doesn't really matter, but that's a convention and it's good if you stick to it. Okay, so that's that. And of course, it would be the other way around if you have, for example, the transpose of nu mu, for example. Of course, you just go back to mu nu. Okay, so that of course makes sense. Now, just like we did in the case for the rotations, we would like to check, what's up with the deal. Like before, we saw the transpose of the rotation matrix times the rotation matrix ended up being just the identity. So, well, what's going on here now? So what if we take the transpose of the lambda, of this lambda, right, our Lorentz transformation, and we multiply by just a Lorentz transformation. So here we have to be a little bit careful because there's a lot of indices. So we want to make sure that we are just consistent with what it is that we do. So for now, I'm just going to write this without any indices. This will give us this sort of Dirac delta, and I will prove it. I will prove it in a moment. So let's just choose whatever parameters we want to be the ones that remain. So let's, for example, say that we want this to be mu lambda. It doesn't matter which one, just choose whatever Greek letters you like best. So what we will have is 2 lambdas. And since this is going to be this multiplication, we need to add, right, have this implicit sum over some index that is not going to be in the end result. So we can use nu and nu. Okay, so they of course have to be like right next to each other. So we have nu, and I actually need a little bit more room here. So I'm gonna move the lambda to the side a little bit. Okay. And now we just have to choose what we want to call this. So we can call this, for example, nu lambda, for example. And this right here, this is going to be, depends how you write it, right? You can write this as the transpose. So transpose of maybe mu nu, so that in the end, the nu's contract and we end up with the mu nu. Or you could just write this explicitly, right? You can write this as lambda, and it would be nu mu lambda nu lambda. Okay, so both of these forms are equivalent, but if you're going to multiply through, this expression is maybe a bit better because that way it is a bit more intuitive. You can see the resemblance with the previous form of writing this down. Okay, so let's now actually multiply this so that we can see what's going on here. So we are going to be multiplying this lambda, which we already know what it looks like, with its transpose, which we also know what it looked like. Okay, so let's see. So we just multiply here, and what we get is the following. So this product would be, now what is the transpose? We just found it. It is the hyperbolic cosine, or cosh, times sinh omega, not times, sorry. Sinh is just right next to it. I don't know why I said times. So cosh omega 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. And now we multiply this by just our regular Lorentz transformation. So cosh omega minus sine or sinh omega minus sinh omega cosh omega. And then we have 0, 0, 0, 0, 1, 0, and then 1 again, 0, 0, 0, 0, 0. Okay, so from here, well, we just multiply. So let's multiply through. So we have cosh sinh times these things. So cosh squared we get cosh squared of omega minus sinh squared of omega. Then we have right underneath, we multiply this row times this column as well. So there we have sinh cosh minus sinh cosh, so 0. And we still have 0 down there. Then in the next one, we get the first row times this column. So we get minus sinh cosh plus sinh cosh, so also 0. Then right underneath, we get this times this. So we get minus sinh squared. So minus sinh squared of omega plus cos squared. 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. But what are these things? This is simply 1, right? It's one of the identities of the hyperbolic trigonometric functions. And this right here is also 1. So there we go. We just got, as a result, the identity matrix here in 4x4. But keep in mind that our result does not have to be a matrix. It's supposed to be just a number, right? So we are just fully contracting these matrices. We want to get delta mu lambda, right? We want to get the mu lambdath element, right? So that simply means, right, if we have delta mu lambda, that simply means come here to the muth row, to the lambdath column, and just take the index, so just take the element, right? And it's going to be 1 if they are the same, 0 if they are opposite. That's why we use the Dirac delta symbol right there. So we can see that the transpose of the Lorentz transformation is its inverse, which means, of course, that the Lorentz transformation is orthogonal, just like the rotation was before. So now that we showed that, let's go ahead and expand our Lorentz transformation in terms of, you know, these infinitesimal components. So if we have lambda mu nu, for example, we can write this infinitesimally. Okay, and how do we do it? Well, we know that we can write this normally as, I think I may just copy it. I've written it down a few too many times, so maybe I'm just gonna copy this. So just copy this, Control C, we go down here, get rid of that, and Control V, and just put it there. Okay, so now infinitesimally, right, what is this? So infinitesimally, cos of omega, if omega is very small, right, so now we say omega is very, very small, well, that's simply 1. Sinh is simply going to be omega at those very small values, with which we will call epsilon like before, so we get minus epsilon. Then we have, of course, here minus epsilon again, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. So this we can write as our delta mu lambda, just like before. And then we have plus this other matrix here, which is 0 minus epsilon 0, 0, 0, 0, 0, 0, 0. A bunch of zeros. Okay, and that's going to be, of course, the very interesting part here, right? Those deviations from the identity, but we will go into that a little bit later. For now, I'm going to just hint at that. And this thing here, we can just call, let's say, epsilon mu, in this case, to keep with the notation, let's say mu lambda, right? So that's going to be that matrix. And we can also now find, for example, from this, we can find, so this is epsilon, that is epsilon mu lambda, and we can use it to find, for example, epsilon mu lambda up there. How do we do it? Well, we just need to raise the lambda index there. So we just multiply, right, by eta, and now if we want to raise it, we should do it like this. We should write it upstairs. Let's use a dummy variable. So of course we want, I don't know, let's say nu or something, and then lambda. And then we multiply this by epsilon mu lambda. So by multiplying through, we're going to get what this looks like. So of course the metric is 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, minus 1, 0, 0, 0. And we multiply by, whoops, I intended to copy this. We multiply by this, right there. And this is going to be, so we multiply this by this. So we're going to see, well, since the only non-zero element are those two, those are also going to be the only non-zero elements. So let's only calculate those. So that element right there is this times this. So we get 0 minus epsilon 0, 0. And this element is this row times this. So we end up getting plus epsilon. And a bunch of zeros. Okay, so that is what epsilon mu lambda looks like, written like that. And we can see, of course, that epsilon mu lambda is equal to minus epsilon lambda mu, right? It is anti-symmetric. And of course, note that what we did here basically is just change the rows and indices. And yeah, that's not transposing, right? Keep that in mind, that's not transposing. Okay, so that's something to keep in mind. We will come back to this result in a later lecture once we start diving into the covariance of the Dirac equation. So now let's move to something else, because we have now talked about the Lorentz transformations. Let's talk now about Lorentz invariance. So Lorentz invariance is something we have talked about, and the whole point behind it is that we want physics to be the same everywhere. It doesn't matter where you're looking at physics. The whole point is that it has to be the same regardless of where the observer is, how fast you're going, and things like that, right? So for that reason, we have kind of a way to check for Lorentz invariance. And what we do now is we say, if something is Lorentz invariant, then what we want is that its length shouldn't change under a Lorentz transformation. If that is true, then that object is going to be Lorentz invariant. How do we write the length of something? Well, that's simply the inner product, right? Let's say eta mu nu or something, that's kind of what we always use, times x mu x nu. Okay, so we want this product to be exactly the same for our new set of coordinates x prime mu x prime nu, right? Where we consider that those coordinates, so x prime mu, of course it also counts for nu, is going to be lambda. And here, of course, we have to keep in mind, if we are left with mu at the end, we need mu up here. And then we need some dummy variable here, or some dummy, not variables, or index. And then we multiply by x lambda. So when this happens, these two contract and our x will end up with mu. Okay, so this is what it looks like. Of course, for nu, it's the same, but with nu. Okay, so now what can we do here? We can analyze this a little bit. And for example, one of the things that is very interesting here is just to multiply a little bit, just to see some further properties. So for example, what we can do is just take this expression and just plug this in, right? So by doing that, we get eta mu nu x mu x nu. This is equal to eta mu nu times lambda mu lambda, a little bit confusing perhaps, x lambda, and then lambda nu. And I guess here we're going to have to be a little bit careful in terms of naming. So we can't just call this lambda again, otherwise it's going to be confusing. So I don't know, rho or something. And x rho. Okay. All right. So now what we can do is rearrange here, because this lambda, whoops, I didn't include it. This lambda is simply going to be a number, right? It's the new row element of the matrix. So of course it commutes with the lambda element of that x vector. So this would be lambda. What were the indices again? It would have to be, I guess, nu and rho times x lambda. Okay, so this is how we can now rearrange it. And this means, of course, that now eta, and I guess we can now change the indices here so that they match the ones that we are going to end up with. You know, they're indices in the end, so there's a certain freedom there. So we can say eta lambda rho has to be equal to eta mu nu lambda mu lambda lambda nu rho. Okay. So this, of course, assuming that we already changed our indices here, right? So this is lambda rho x lambda x rho. So of course you can see that those are already the same. So we need this to be equal to all of that. Now this is something. This is already a very important condition, right? This has to be true for something to be Lorentz invariant. And this is very interesting because we can now check this, and it's a decent multiplication exercise. So what we can do, and if we want to multiply something, we need all the indices to be right next to each other, right? As we have said. So let's just commute these two elements. So we get lambda mu lambda times eta mu nu times lambda nu rho. So the nu's are right next to each other. The problem is that here this lambda, well, they are not right next to each other. And here this is mainly for us to be like very sure. In principle, you could already do this if you know which form of these matrices to choose. But here lambda, mu lambda here, you can take the transpose of the transpose, right? The transpose of, now we switch these two, of lambda mu. And here we can see eta mu nu, lambda nu rho. So indeed, now we see that all of our indices are right next to each other. So that means that we can totally just go ahead and multiply. So we expect that this is supposed to be true, right? We're just going to check it. This is going to be equal to the transpose of the transpose. So, well, that's simply going to be our, our transformation. So this would be cos omega minus sine or sinh omega minus sinh omega cos omega, and then a bunch of zeros. So 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. Then we multiply this by the metric. So 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, minus 1, 0, 0, 0. Okay. And now we need to multiply this by another Lorentz transformation. So just take this, Control C, Control V, and we just put it there. Okay, so with this, well, we now just start multiplying. So multiplying this first two matrices, we get cos, so just cos first, so cos omega minus, then we have cos times 0 minus sinh times minus 1, so we get plus sinh. Then we have minus sinh times 1, and then we have minus cos. And everything else remains the same. Except actually for these, so we get minus 1 and minus 1, of course. And then we multiply by still the same Lorentz transformation matrix. So now we multiply this. So by multiplying this, we get cos squared minus sinh squared, which is 1. Then we have down here cos, so this would be, minus sinh times cos, and then plus sinh times cos, so 0. And here it's still 0. Then in this slot right there, we get minus sinh times sinh, so plus sinh squared, and then minus cos squared, which is minus 1. 0, 0, 0, 0, 0, and of course, minus 1 times 1 is minus 1, so those remain the same. And this is exactly just our, what's the indices that I used? Lambda rhoth elements of the metric. So, there you go. We did indeed prove that that is indeed true. Just explicitly, it's a good exercise to understand that everything that we are seeing is simply a matrix, right, and its elements, so that you have a good understanding of it. Now, let's go back to an expression so we can continue to study the Lorentz transformations, because we talked about this expression right here, right? So lambda nu mu nu lambda, this thing right here, this we said is equal to delta mu lambda. Okay, so let's take this and kidnap it and just take it very far away. So let's just go to somewhere else here so we can study some more properties. In particular, what we would really like to talk about is to see the determinant, for example, of this. And also just talk about some of its elements, right? And you will see exactly which ones concern us. So one of the most important things we care about is seeing what's going on with the element time, right? What's going on with time. So for that, which element is going to correspond to time? Well, the 0, right? So 0, 0, and then we can just see what happens with the other ones. So what I mean here is, let's take a look at mu equals 0, lambda equals 0. Okay, so let's take a look at this expression when this happens. So when that happens, we have lambda nu 0, lambda, and now nu, and this small lambda is 0. So this is what we have. And this has to be equal to the 0, 0th element of this Dirac delta matrix, which is simply 1. Okay. Now, what's going on here? Now, and you can now see much clearly that this is indeed going to give us a number, which is what I have been promising you so far. Now we can separate this because nu is 0 I, right? It can be 0 or 1, 2, 3, which is inside of this I, 1, 2, 3. So let's separate that because this is an implicit sum. So let's take the first element, the 0, 0th element, times 0, 0, and then let's just say plus the rest of the elements, I, 0, I, 0. And this, of course, has to be equal to 1. Okay, so of course, well, lambda 0, 0, lambda 0, 0. What are those? Well, let's go back, bloop, 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 and take a look at what those matrices were. Right, so lambda mu nu was, this would be this first element, cosh omega, right? And what about its transpose? Well, its transpose, I believe we have it somewhere up here, right? Its transpose is this, and the 0, 0th element is also cosh. So it is the same element for both of them. So you can just choose any of them and keep that as whatever you have written down. I personally like to keep this one, but it doesn't matter. So this squared plus this thing. Now let's do the same for the I 0th element, right? So what's going on with the I 0 element for both of them? So for example, here, what is lambda I 0? Taking a look at this. So lambda, now this would be I 0. So I goes 1, 2, 3. And this here refers to rows, and this here refers to columns. So we are saying rows can be 1, 2, or 3 because there are 3 different terms here. So rows, so that would be row 1. So these 3 rows, but only the first column. So only these values. Okay, so those are the values that we are talking about here. And we want to see what those ones are. And actually, we have to be a bit careful because I said I, which means it's actually these 3. Okay, let me just put it there. Why? Because this is 0, right? So this is 1, 2, 3. So these are I. So when we say lambda I is 0, the only possible value here is minus sinh omega, right? All of the other ones are 0, right? But of course, if we want to keep this general, we don't really want to specify which of those rows are 0, because then we're saying, oh, then we are doing a transformation around this particular axis, and we want to keep this general. But keep in mind, only one of them is going to be not 0, and it's going to have a value of minus sinh. Now let's go find the transpose and do the same thing. So here's the transpose. Now if we want to see lambda I 0, again, this means our rows 1, 2, 3, so these, and also only the 0th column, right? So these 3. So the only non-zero possibility is sinh omega. So the point here is that lambda I 0, this is going to be equal to lambda I 0. Okay, so let's just go back and plug it in as well. So here again, we can choose any of them. Let's just keep this consistent, right? We don't want to keep a mix between the transformation and its transpose. So let's just keep this one. And this would be squared, but with a minus sign in front. So this is minus. So from here, we can see that lambda 0 squared is equal to 1 plus lambda I 0 squared. Now this value is always positive, right? It's squared and we don't have any complex values inside of our Lorentz transformations. So it's always going to be positive, which means that here we have 2 possibilities, right? Lambda 0, 0 has to be greater or equal to 1 for this to be true, or lambda 0, 0 has to be smaller or equal to 1, to minus 1, sorry. So those are the 2 possibilities. These are the orthocronous. It comes from ortho, which is straight up, and chronos, which is time. So it just means that this is straight up in time, right? It's a transformation that doesn't change basically the direction of time, which is what this does do. So these are the orthocronous Lorentz transformations. Okay, and those are the ones that we are going to be interested in the future. even though, of course, the other ones can also be interesting in some other situations. Now, another important thing, which we can actually also derive from here, is going to be the determinant. So what is the determinant of these matrices? Well, let's see. Let's take the determinant of this equation. So the determinant of this is equal to the determinant of this. So determinant of delta mu lambda. Now, what is the determinant of this? Well, it's the determinant of lambda nu mu times, right? This is properties of the determinant, lambda nu lambda. This is equal to the determinant of 1, 1, 1, 1, 1 times 1 times 1 times 1. So this is simply 1. Okay. Now, both of these are going to have the same determinant because of the fact, or can have the same determinants because of the fact that, well, they're both still Lorentz transformation. One of them acts on the covariant vectors, one of them acts on the contravariant ones, but in the end, they are going to have the same ones. So in general, this is going to be just the determinant of lambda, and I guess we can drop the indices. We are not really going to use them anyways. Determinant of lambda squared, which has to be equal to 1. Now, what does this mean? Of course, this means that the determinant of lambda is either plus or minus 1. Okay? And of course, as it turns out, we are going to be a bit more interested in the ones when the determinant is 1, which are known as the proper Lorentz transformations. And if you consider a determinant of 1 and also that lambda 0, 0, or I guess lambda, if you did it the other way around, 0, 0, whatever which ones you take, right? If you consider that as well, then you have proper orthocronous, right? This has to be greater or equal to 1. Then you have proper and orthocronous Lorentz transformations. Now, why are we going to be so interested in focusing on the proper orthocronous Lorentz transformation, which means when we have determinant of lambda equal to 1 and also this condition right there. So the reason why we are so interested in that is because building on that, we can get all other kinds of transformation, right? All other possible combinations simply by applying a combination of space reflection or just time inversion. So what do I mean by that? So let's say we have some lambda transformation, right? And we can separate this basically into a transformation on the space coordinates multiplied by the proper orthochronous lambda transformation that we already have. So this space transformation would simply be 1, 0, 0, 0, 0, 0, minus 1, minus 1, 0, minus 1, 0, 0, 0, 0. So don't confuse this with the metric. All that this is, so times lambda proper. All that this does is saying whatever your x is, multiply it by minus 1. Whatever your y is, multiply it by minus 1, right? And so on. And so all you're doing is just doing this this space reflection operation. Okay, you can do something similar. For example, if you want to do a time reversal, right, which means when t goes to minus t, what we just did, by the way, is when x, the x vector, goes to minus x, right? And in this case, we would just have a time inversion times lambda proper. So this would be simply minus 1 and then 1, 1, 1 and a bunch of zeros times our lambda proper. Right, so in this case, here we would have, of course, that lambda 0, 0 would be minus 1. So you can see that now we are in the other case, and the determinant would end up being minus 1, right? Since the determinant of the product is the determinant of each one of the elements. This has determinant 1, so maybe we write like this. So the determinant of that is equal to 1. The determinant of this would be minus 1. So the transformation itself here would have determinant minus 1. Now, in this other case, for example, you also have determinant minus 1, but your lambda 0, 0 is 1. So you can see that we are now going through the other possibilities, right? So we have the case where you have determinant minus 1 and lambda 0, 0 minus 1. We have the case we have lambda 0, 0, 1 and determinant minus 1. And of course, we can go for the combination basically of these two, where we have inversion in space and time, so where we have our transformation as lambda of space and time times our lambda proper. And this would be simply a matrix -1, -1, -1, -1 times lambda proper. So there we combine both of them, right? Here the determinant would be 1 and lambda 0, 0 would be -1. So there you can see that just by focusing on this one group, right, the proper orthocronous lambda transformations, we can use any other ones if we ever find the need. So that is the most important thing that we need for now about the Lorentz transformations. We will of course continue to learn more about them in the videos that will follow. And yeah, I mean, if you enjoyed the lecture, please consider leaving a like on the video, commenting and subscribing, and maybe even consider checking out my Patreon so that I can spend a little bit more time developing these lectures. So I hope that this was useful to you, and I'll see you in another video. Thank you very much for watching.